The future is here already. It's just not evenly distributed. Yet. Today's world teems with innovation. The nexus of hardware, software, and human ingenuity promises a revolution in possibilities. What does tomorrow look like? Witness Future Proof.
Ladies and gentlemen, hello and welcome back once again to another episode of Future Proof. Your host here, Eric Kavanaugh, and I'm so excited to have on our show today a key inspiration for the show itself and the title and the content and everything we do here, Mark Madsen of Teradata. He's the guy who turned me on to the quote from William Gibson, "The future is here already, it's just not evenly distributed." And I can tell you, Mark is not only a genius, he has the best PowerPoint slides in the universe, and we've checked on Mars and Venus or a couple of places. No one's better than Mark. With that, Mark, take us away, future-proof, looking beyond today's analytics.
What we're kind of going to talk about, Eric and I, today is things related to the future and how one thinks about and how one plans and how organizations plan and make decisions, because that's what's really, at the end of the day, involved in everything we do. So I'm going to start this with a little story. So once upon a time, there was a company called Ford Motors, and Ford Motors made cars. And in the 1950s, they made a concept car. And it was an amazing concept car. It could go 1,000,000 miles on one charge. It had a top speed that was only gated by the electric motors that you put in that car. It was an all-electric vehicle, right? We're talking the 1950s. We're talking about a vehicle that could outperform a Tesla or anything else that we had. And the reason that it could do this is where you see in this picture of the car, it was called the Nucleon, was the nuclear pile that sat in the back. Your power source was a nuclear reactor. And the reason for this was that in the 1950s, nuclear was great, right? If you wanted power, nuclear, right? We had radium in gum. And we had it in gum because radium is energetic and it gives you energy. So let's paint it on watch dials and let's put it in chewing gum. And radioactive stuff was everywhere in the 50s until everybody started getting cancer and dying. And then we realized that maybe that wasn't such a great idea. Right? This was just a problem where they took one thing and linear extrapolation and didn't think about all of the other effects, right? Like biological effects. So the reason that there's that dark black tinted screen is the leaded glass in the passenger compartment so that you didn't sterilize the driver and lose new consumers and buyers of your car. Never mind the mini Chernobyl effect every time you were in a car accident at speed. So of course, this was a technological failure. And that kind of brings up one of my favorite quotes about not just automobiles, but everything, which is that if the car had followed the same development as a computer, a Rolls Royce would cost $100, get 1,000,000 miles per gallon, and explode once a year, killing everyone inside. The genius of Cringely's quote is that Ford got that in the Nucleon in the 1950s already, but we forgot about it. And so, if you are in management, you really should understand the time anything reality curve. Right? There is always a limit to the system. Nothing is linear. If you step on the brakes, your car slows down. What if the pavement's wet or icy? You keep jamming on the brakes and you start to slide, right? There are points where application of force or effort into a system send it into the limits of that system, and then it behaves in ways you don't expect. What we've been doing with AI is we take it and we shove it into things like a Tesla, and it drives down the road and it thinks it sees a shadow and it hits a deer. That's your AI's results when it gets unexpected data. And AI is learning and being trained on an environment in a statistical way, and the results of the AI end up being, well, unexpected. You don't know what the behavior is going to be because you've hit the limit of the AI, because the AI itself is a system. But in reality, what you fail to see is the bigger system. The database is itself a complex system, and then people pile data into it and do things with it, and that in itself is yet another system hiding the system that sits below it.
Mm-hmm.
And yeah, it takes to uncover all the edge cases to make a solid, robust, performant database takes about 10 years. And that's just to get it to a reasonable state. It takes even longer to get something that's as good as SQL Server or Oracle. In the analytics world, Teradata is 40 years old. Companies aren't machines. Companies are complex systems of processes and people and external inputs we have no control over. And so, all those stories in that MIT tech review about AI gone wonky with recommendations or supply chain optimizations are because we treated it that way. We treated it as if business as usual is always business as usual, and it never is. AI is not a miracle cure because it's based on statistical learning. And statistical learning is just a fancy way of saying, look at what the most common things are in the past and extrapolate them forward and build your behaviors on it. And so AI was taking the statistical model, whether it was a deep learning model or something else, building it into an application. So Google had a good research blog recently where they talked about a real problem, which is diabetic retinopathy. It can take 6 to 8 weeks to get an image from a place to an expert to have it read, do all these things. So Google said, hey, let's do AI. Let's do deep learning and AI, and we'll use our image recognition stuff. And it's great that they did this. They built something that in general works on the images better than a human being does at detecting the signals that are symptomatic and leads to a higher diagnostic rate. But the other thing that they were doing this for is that if I can do that, I could take the human who has to interpret the images out. That is the no-no, the mistake that we made in the 1980s when I was working on blood diagnostic expert systems that were going to replace doctors doing exactly this, diagnostics in medicine. You can't do diagnostics in medicine because there's so many secondary things. If you try to replace the human judgment, you make mistakes.
And that's the key, right? Is that what are the critical components of this ecosystem? The nurse practitioner, the internet connection, the location, the equipment that they're using, all of these are control points that have to be considered and worked into the process.
Yeah, exactly. That's exactly it. The control points and the feedback. Well, it only works when it's well understood. And when it has a lot of interaction points like that, you have to design upfront that into your software. Things can come out of nowhere and tackle you. I think that is universal, right? It's not just AI or software data, it's everything. We get ourselves trained into business as usual. And business as usual is this nice flat line. And then when competition increases because things change, because the market changes, people's tastes change, behaviors change, the pandemic happens, and things go all pear-shaped. Your decision-making can't be this far out. And the biggest problem we have in our economy, especially in the financial and banking system, is hyper-optimization. Our supply chains are optimized to within an inch of perfection, assuming that nothing untoward happens. Minor disturbances we deal with, major disturbances we don't. And then the so-called black swan, suddenly everything goes pear-shaped and it's all wonky and it looks like this, suddenly that nice flat line is all over the place. And then you can't make a decision that's even a week out, right? Let alone 3 months out. So forget strategic planning, forget tactical planning, you're in reactive mode. If you make a decision in a very narrow time window, assuming one thing, and suddenly you hit the peak of that curve, your arrow goes a different direction. In times of stability, we think of stuff like profitability. And everybody thinks, well, we can just have, a little bit of quality, our leadership and how we, have happy employees and whether our cost structure is good and the competitors are known. And all it takes is a competitor to do something different and your model's broken. The completely backwards model. Get Tableau, get a spreadsheet, slap some data in a lake, and they're all simple models. But the reality underlying that is that you just built a little bit of data around a very simple understanding of something, when in fact there's a bunch of data with a bunch of connections, and you need to be able to connect that information. If you understood the system as a system rather than as the simple linear thing that you do in the spreadsheet, you would have done things differently. You would have made different decisions, right? that's the, that's the complex pandemic model of response versus a simple model of response when it comes to something like economy. And I know you'd wanted to talk a little bit about that.
Yeah, well, you just gave us a classic example of penny wise, pound foolish. That's like as good an example I'll ever have. And that's great.
That is actually, every old aphorism has its roots in something like this, right?
Yes,
It
that's
gets
right.
boiled down into that, and that's exactly right. I think my favorite one from systems theory was a stitch in time saves nine, right?
Right.
If
Yeah,
you stitch that hole in your shirt, you'll save yourself a lot of work later.
that's exactly right.
And a friend of ours, Dave Wells, had these similar thing, looking at business questions, and he couched it in terms of uncertainty, which is the same thing. Complex systems are very hard to think about. Linear systems are really easy to think about, so we gravitate towards them, and we make Tableau dashboards that look wonderful, and we build spreadsheets, and they're great. But they're simple and they're understandable, but they hide the uncertainty. Somewhere in your data or in your model, you've abstracted away reality. And he points out that a lot of times economic cycles that are good tend to get to business as usual and optimize things, and uncertainty is low. And the economic cycle is at peak. But when the uncertainty is high, you're losing money. You don't know why you're making money. You don't know, what's going on. So when it's peak, what happened, what's going on, simple dashboards, data warehouses, and when uncertainty gets really high and the economic, trough hits, you're trying to figure out what's happening right now and how can I change it and how can I influence it? Those are systems questions, right? How does the system behave when I take an action? And so I always liked, his idea that, when it's high uncertainty, you're going to model and simulate. You're going to do analysis. You're going to try things. Welcome to the world of data science, right? Welcome to the world of analytics. Welcome to the world of basic human analysis. Whereas when the uncertainty level is low, you have goals, you have targets. You measure to the target. You track numbers in your transaction systems into a warehouse that shows up on a dashboard. Two completely different ways of approaching problems depending on your understanding of which problem you're facing.
Mm-hmm. That's right.
So I always liked that, and the thing is that brings up that we ignore all the stuff we used to know. There's a big difference between not having the wheel and between having the wheel and ignoring it for some dogmatic reason or because you're stubborn or because you don't understand. We knew all this stuff. We knew the AI stuff when I was working on it. I had to stop working on it because it didn't work in the late 1980s. And Google AI research had to spend God knows how many, tens of millions of dollars to rediscover the same fact we already knew and how to approach solving it. The same thing with tech, people buying technology, people throwing away databases for 10 years. Now suddenly databases are the hot commodity. Gartner says that databases are growing at over 20% per year now. Meanwhile, all the stuff we talked about for 10 years in the NoSQL market and the cold object storage market are falling into the toilet. But in organizational terms, which is where I want to keep this, systems, right? This book, the genesis of this book, which was written in 1993, by the way, by Donella Meadows, her original essay was basically, thinking in systems, points of intervention in systems. There was an essay she wrote, which was, we intervene in economic policy or in our supply chains or in making a city more livable or in healthcare without understanding the system as a complex system. And so there's a whole discipline around thinking about these things in a different way. Everything you and I have spent our last 20 years in our careers on in the data world has not been built on the foundation of this kind of stuff. And it's sad, but it's true, right? And I loved some of the work that they've been doing. This is from there's the Donella Meadows Institute, which has free copies of these books, and they had the guy who did the How Things Work books, and he did some wonderful work on this, and he said, look, you look at a thing, you're not sure what's going on, uncertain, ambiguous. You step back, you get the big picture. Then you start to see the pieces. Then you look back again and you see how those pieces relate. And then you look in. It's a constant going back and forth. it's not business as usual, right? It's not data, which is a shadow of reality. You have to constantly change those things around. And so it's time to start looking at these things again. And these things are old. 1960s for this, but you know what? A lot of this was based on what was called cybernetics. Cybernetics was big in the late 1930s. So, our example would be like a supply chain, which we're having a lot of problem with, especially in the US right now, because we've hyper optimized our supply chains to be very fast and very efficient, which means the system is very narrow, which means that small perturbations out here take you out of the normal limits of the system, and suddenly in that S-curve, you're skidding out of control. This is everything on the left-hand side, from milk flowing through dairy processors to warehouses, distributors, to cheese manufacturing, to distributors, to wholesalers, to retailers, right? It's the whole supply chain on the bottom, and the top part is the information flows. These are all the points where communications are moving, and the gray arrows are all the actual physical goods movements. And the information flows and the physical good movements, they're all coordinated, and there's feedbacks. And, oh, you didn't ship us enough, you were short, you send this feedback back, another piece comes out with a different truck, and all of that stuff has all these cycles and feedback loops. Try and figure out what happens if you remove one gray box in this, right? What happens if you take one of the red things, which is information transmissions, and kill it because the distributor went bankrupt, right? This is what is happening throughout the world economy, not just national economies, not just individual industries, but worldwide. It is a hyper-complex system made up of systems. The economy is systems of industries, which are market segments, which are individual companies, which, it just works its way down both geographically and organizationally. Turtles all the way down.
That's right.
And the problem is that our apprehension is wrong. We keep thinking it's just the number of things. No, it's the number of connections. Like, you and I have used rock, paper, scissors before to make decisions about who gets to go first. Well, sometimes rock, paper, scissors doesn't work. So you got to do rock, paper, scissors, Spock, lizard, which is 5 things. But there's a lot more connections. You have to memorize a lot more because, does the lizard beat Spock? Or does Spock beat the lizard? Because Spock could hit the lizard with a rock, but that means rock beats lizard and not Spock, right? That's thinking in systems, right? It's not the number of things, it's their connections that makes it so hard. And so you got to think about things differently. And so, yeah, that's what we're really dealing with.
Yes, in our final minute, I'll just kind of comment that you've done an excellent job of explaining why complexity matters. And the fact is you need a more dynamic foundation, just like the newer buildings in San Francisco are built to handle earthquakes, right? Before we couldn't handle earthquakes, they built special foundations to deal with that. And that's kind of what you're talking about, right?
Yeah, absolutely.
That is just fantastic stuff.
You
I love it.
You mentioned something to me. Actually, don't really have a slide for it, but this all goes back to organizations as systems of people, right? And supported by computers and other things. And we don't think about organizations that way, and it all starts there. And so how we make decisions and how we think about this, the people elements and the computer elements and the systems elements. And you had mentioned, working in the banking industry and what that was like.
Yes, and my friend, I think it was from Wells Fargo, was the chief risk officer, and he said after the financial collapse of 2008, because he actually distributed TARP funds, so he knows exactly precisely what that felt like, and it could not have felt good. And his musing joke was, "Oh, I now have a much greater appreciation for macroeconomic risk." Like, yeah, like it can bring down the whole system and everyone gets screwed. That kind of risk, right?
Right. Yeah. The example of the system with the debt stuff here into the banking system here, which goes across country boundaries here. At some point, everything is interconnected, and we always try to simplify things by ignoring the connections, and that tends to send us wrong. So we have to think about these things in different ways. And I think what we're going to see now is a deflection in the AI market and the data and analytics market, which is going to be back to basics. Wait, AI is statistical learning, which is business as usual. And we don't know enough about dealing with business not as usual for that stuff to be really useful. The human element is going to come back in with a vengeance means a lot of the data stuff is going to come back in, which means a lot of the databases stuff comes back in, which I mentioned our friends at Gartner, and they're pointing out that somewhere over 20% growth in database market is bearing this out.
Wow. You can see why we got this guy for Future Proof.
Thanks, Eric.
Thank you.
I'm going to talk a little bit about edge computing, and it is not something you probably worry about today, but you will worry about tomorrow. And I think there's already enough buzz around it, and let's try to demystify this some. What is edge computing beyond the buzzword? Let me give you a simple example. So let's say that you went to you heard about a great cafe, this, we'll call it the App Cafe. You go with a friend, and you read the menu. Wow, this looks like amazing food. The server's there, takes your order. Wow, let's get some food. Well, all of a sudden you see your server driving off in a car or a delivery van. And you're like, what is going on here? Why is this person leaving? Well, the reason they're leaving is because the kitchen for that cafe is actually farther away. And that's Cloud Kitchen. And so the server is then delivering the order to the kitchen. The kitchen then spends the time to make it, and then puts it into the delivery van and sends back with the wait staff. Wait a minute, I ordered soup, not a salad. Oh, no problem, I'll go get it. If you actually went to a restaurant or a cafe and you saw this happening, I'll bet you're probably not going to leave a very good Yelp review. Edge computing, distributed computing, yay. But it's this whole thing about computation and data storage, and the key here is closer to the location where it's needed. And that, I think, makes sense in a lot of people's minds, because going back to our restaurant analogy, edge computing is like having a kitchen in every restaurant, which sounds really obvious. But we don't build our computer networks and how we do applications like that right now. What's driving this new future? Networks have become a lot more ubiquitous, and the capacity is becoming more ubiquitous. This is a good example of now we have the potential, when Starlink finishes, we'll have the potential of having good quality, high-speed networking in any location on the planet mostly. This is the future, and this is something we have to think about. And there are other efforts as well. I think Facebook and Google have all been trying to figure out how to to gain access to new markets based on ubiquity of networking. It opens up the door for whole new audiences, but it also gives a better high-speed internet connection to someone who may not even have an internet connection. 5G, again, is not revolutionary, it's evolutionary. And what 5G is supposed to be trying to address is, if you look at the networking, the data networking that is attached to the cell phone networks, it was really an afterthought. 5G took that from the beginning and said, data is the first class. And so it's addressing things like latency. Talk to anyone in the cell phone industry, this is it. This is what they're all working towards right now. Compute capacity has changed. And this is just Moore's law, but we're putting more compute capacity closer to everyone. It isn't all just centralized. The biggest clouds, for instance. It's easier to get compute capacity anywhere you need it. We have enormous amount of workloads coming that just will not be okay with centralized computing. A good example is, of course, intelligent roadways, self-driving cars, the thing that's turning into the fusion thing. It's 20 years away. But it's not. Networks need to be closer, the data needs to be closer, and these workloads need to have really, really low latency. We'll cover that in a minute. Why is edge computing even becoming a buzzword? It covered these things that were like, look, here are 8 things that everyone thinks is true and get you in trouble. Let's focus on just 4 of those. And that is, the network is reliable, the latency is 0, bandwidth is infinite, and transport cost is 0. In the world of distributed computing, these are easy assumptions to make. Well, if I connect up my Ethernet cable or hook up my Wi-Fi, then everything is instant. It's instant-ish. My power went out. And what does that mean? Well, I lost my Wi-Fi immediately. Just knowing that the network isn't reliable, I'm not going to count on the fact that only thing I can ever use ever is my Wi-Fi. We live on a big planet. It's kind of huge. And when we talk about the speed of light, it isn't instantaneous. And at large distances, it can actually add up quite a bit. Now, this is showing you to go around the Earth in a vacuum, it still takes light 133 milliseconds to go all the way around the Earth. It does introduce some latency, and you can't beat that. We made it worse. We transmit a lot of our stuff over copper and fiber. And the reality is, based on physics, 70% of that, you get about 70% of the actual speed of light from that. And with networks and being able to relay and routing and all those things, it's double. So that means around the world is actually 266 milliseconds, which is a quarter of a second. These are things that when they add up, they start making some really bad things, and you can't beat it. When someone is communicating with a central application and they're talking to that application code, we have a few things here. The law that we should think about is like the greater the latencies, you're going to get less user satisfaction. Less user satisfaction means less dollars. In terms of mission critical applications like medical or self-driving cars, logistics, that sort of thing, that greater latency could actually be deadly. That needs to happen in single-digit milliseconds. And going to cloud provider, like renting in an Amazon container somewhere and coming back and saying, yeah, you're totally going to get into an accident. Hold on. By then, I probably have had that accident. And at that point, I'm going to be asking for help. Thanks, cloud. Now, that means the central computation and data storage paradigm is now super challenged. If I have a San Francisco user versus someone who's like in Sao Paulo, Bangalore, London, where's the central point in that? At some point, someone's not going to be very happy. And that just doesn't work anymore. The only way to beat the speed of light is to just accept it and get things closer. And this is where edge computing is really showing its prowess. A San Francisco user has local computation and data storage, and so as a Bangalore user, they're going to have a pretty similar experience because now they're dealing with a sub 10 millisecond latency. Regulatory issues now are by government to government. Yes, we can create pipes and we can route data from one point to the other, or maybe not, but there's going to be rules on that data. And in some cases, those rules are things that can not just get you in trouble, but completely shut you down. Working around regulatory issues is really about edge computing at this point. This is the next thing beyond cloud. We went from on-prem to cloud. We're going to go from cloud to edge. If you look at companies like NVIDIA, they're not just selling graphics cards anymore. They're trying to figure out how to embed like a high bit of computing, so parallel computing inside of a car for what it needs to be a self-driving car. If you have a global business, your data has to be global. Reliability is an important part of whenever you do distributed data storage and how you make this ubiquity of your application. And reliability is really built around this idea of like, I can have these problems that come up. For instance, a partition problem.
Hop online to insightanalysis.com for more information. That's where we'll post the archive. And folks, we want to know what you want to know. So if you have any thoughts about all this, send me an email, info@insightanalysis.com. That comes straight to me. And like I say, we're keen to understand what your impressions are. We want to know what you want to know. Send me an email, info@insightanalysis.com. With that, we're going to bid you farewell, folks. We'll talk to you next time. Take care. Bye-bye.